So please welcome Michal Hradiš.
Perfect. Okay, so you know my name. My name is Michal Hradiš. I mostly, the talk today will not be about what I was set to be doing all the time. There will be a little bit about the documents, a little bit about text, but mostly it's computer vision. I've talked with few of you. And if I understand correctly, you have background in machine learning, a little bit in computer vision, but mostly one course in university. I hope my sort of lecture will fit into your needs. I will talk a little bit about some principles of computer vision in general, a little bit at the beginning. Then we'll look at what are the networks and how the basic types of networks for image processing are built, and then some applications. Really weird stuff, even like 3D reconstructions and such, because in speech, it's mostly semantic tasks, like understanding who's talking, what they are saying. There's a little bit lower level, like localization of audio sources and such. But in computer vision, we have much more of that low-level stuff, like understanding what's the geometry of the world around us. It's not just what is the semantics of that. So let's look at the vision in general, how people deal with that, and why vision may be difficult. Basically, vision, if we look at it as like with the basic device which we have, which is a camera, perspective camera, basically just is a pinhole. You have some photosensitive surface at the end, and you have light coming from the scene, going through that pinhole and hitting the photosensitive side somewhere. This is a projective camera. You have 3D world, and you project the scene, the perceived light coming into the camera on a 2D surface. So definitely you are losing a lot of information. You are losing basically, at least you don't know how far things are in the real world. So you can have like many different things in the real world, like this line, this one, this weird surface, whatever, and where they get projected to the surface of the camera, you get the same image, regardless what is the geometry of the real world. Basically, if you see some image, there are infinite number of interpretations of that image. There's infinite number of the scenes which can create the same image. But fortunately, most of them don't make sense at all. And we as humans, we use a lot of either really low-level cues or even higher-level semantic understanding of what the real world is and what it may contain for us to be able to understand it. Like we use simple principles like if things touch in the image, our brains think, hope that they touch even in the real world. So basically, if the person here is touching the Eiffel Tower, sort of, I'm quite sure that you see that it's a miniature of Eiffel Tower, even though it's a real Eiffel Tower. The context is important for us. And there are many principles like that. We understand that objects can overlap, they can hide behind each other. So here, like if you look at this image, how many triangles do you see there? Two triangles. How many triangles are there? Sort of none. Who knows what is triangle and so on. Yeah, so basically you see one triangle, the black one, and the white one even though like it's not there. It just, you hope it's a triangle which overlaps this circle, and this circle, and also like these lines. It could be there. It's definitely not in the image, it's just an interpretation. It definitely could be that you have three Pac-Mans trying to go into a triangular arena and fight to death or something like that. And so, and like for example here you have like, definitely you can see cubes there. Yeah, but for example this image, it's exactly the same, except it's slightly rotated. And if you can convince yourself that, if you can convince your brain that this is a 3D object, then you are very good, right? It's still the same, it's exactly the same, except like in this case, this vertex is aligned with this one. Otherwise it's the same. But because they are at the same place, you can't convince your brain they don't touch. You can't do that mostly. At least most people can't do that. Of course, we understand perspective. Like all the things which I've shown you, they are 2D, that's definitely like flat screen, there's nothing 3D about that. Our brains interpret those images as the real world. For example, here, which car is bigger?
In real life,
I don't know.
I think I guess they all the same, but in real life it will be like the last car.
Okay, can you convince yourself or your brain that these cars are the same size? Can you do that? No, you can't. You can't do that. Yeah? Like, whatever I do, even if I know that these cars in the image, they are exactly the same size, I can't convince myself of that. Like, if you cut it out, you move it around, you'll see that they are exactly the same, but because of the perspective in the scene, you can't get rid of these priors, basically. And it's even like lower level, like, so here you have lines, they are exactly parallel. Yeah, but there's no chance that you can perceive them as being parallel. Like, at least I basically, if I look at this one, it definitely, like, here it's closer, here it's further away, those two lines, and like I can't do anything about it, I see it like that. They are parallel, it's just, again, our brain perceives this sort of perpendicular lines to create perspective, and because of that it diverges. And our human brain and our like visual system go, and like the illusions or the priors and the artifacts of our processing go even lower. If you look at this, I hope it's the correct size. It may be too big, but I'm quite sure that you can, if you move around with your eyes, that you see it's rotating. And there's nothing rotating. It's just really this is artifact. How are our sort of retina and the cells behind that process image information. We understand light illumination. Basically, you mostly don't see colors and light as it is. You don't, what our brain tries to do is to understand the real world, not to just perceive the colors and the information as they come to. So for example here, we understand that there is shadow, there's probably, if this was a 3D scene, there would be a light on the right side. And again, our brain automatically tells us, okay, this box this square A is darker than square B. Yeah, it's how we interpret the image. But again, if you look at the pixels and their colors, they're exactly the same color in this image. We don't, for example, one thing about our perception is that we understand local changes. Like we understand edges and so on. We can't really perceive together this color and this if it's far enough. And again, we understand, our brains understand the shadow and so on. And sometimes it's weird, like we use weird priors to understand images. So here I have two photos. So what's the difference between them? Like if you look at them, what is the difference? Like the main one. Yeah.
Like one seems concept, the other one seems.
So this one has ridges, I guess, and this one has dents, or how it's called, like it's carved in the rock. It's not. They are exactly the same. They are just flipped upside down. It's just our prior tells us, usually the light is coming from the top. So if you see ridge and it's light on the top, dark at the bottom, our brains automatically, without thinking, interpret it, okay, the upper part has to face the light which is going from the top, so it has to be going out from the wall, and the other one is going back, it's in shadow, and this is the other way around. Otherwise, it's exactly the same images. And just by looking at it, you wouldn't have, without this prior, you would have these two valid interpretations side by side. Like both could be dents and could be ridges. And so just understanding the real world in computer vision from cameras, some of it can be done at the level of geometry, can be done directly from simple math, simple geometry, simple lighting things, and so on. But at the end, and you can't interpret the images without prior knowledge. We have a lot of it as people. Historically, it wasn't used too much in computer vision because we didn't have ways how to put this kind of prior knowledge in some machine without writing it down by hand. Now we have neural networks, and of course, even in computer vision, neural networks are the state of the art in, I would guess, all of the tasks you can have. So just very simply, what are some of the very simple principles you can use to understand real world? So one is, for example, shape from shading. This is really no neural networks, nothing. So if you have some assumptions about the object you are looking at, about how it reflects light, for example, that it's not shiny, that it's just matte surface, and you have single point of light and you move the light around, you can compute the 3D shape from that. Yeah, no neural networks, nothing, just simple math, just understanding how surface reflects light if you shine the light from different points. By the way, definitely we as humans use that information. We use this one as well. So this is purely just texture deformation. It's sort of, let's say, uniform texture on deformable surface. We can easily understand the 3D shape behind it. And again, this is some Q. Of course, you could write a code which computes this perfectly for this special case, but we use this information in general to understand 3D scenes. There are some weird, or maybe weird, cues which we can use to understand images, which are sort of lower level even. For example, we can, if you do photography or something, you know that some things can be in focus at some distance because we have real physical cameras. They are perfectly in focus only at one specific distance. And of course, if you change the focal length and you look at which parts of the scene are in focus at which basically focal point, focal plane, then you can understand how far those objects are and you can do 3D reconstruction from that. Just no understanding, just looking which parts of the image are sharp at which point. Yeah, so you can we don't have just cameras. Like in computer vision, we use many different sensors. One of them is structured light camera. That's basically, okay, here I don't need the sound. We have sensors which can shine basically like a pattern into the scene. The pattern is known. It's usually some laser shining through some tiny holes. And camera. Because these points are random, sort of, but random by known, I can find out which part of the pattern I see from which pixel in the image, and just by doing triangulation, I can understand how far things are. And there are even other, so you have set up like this. It can be done with projector or with those dot patterns. It doesn't matter. But basically, you can understand, okay, from the camera, I see this point because there's specific part of the pattern, and the pattern is projected from different viewpoint. By doing triangulation, you can understand where things are. Again, could be simple math. We, as humans, use it in slightly different way. We don't have projectors. We don't shine things in the scene. We have two eyes. So basically, we know where we see an object from one eye and the direction from the other eye. And we can also, to some extent, triangulate and tell how far things are, just thanks to our two eyes. And of course, I don't know if you tried it. You can definitely understand 3D structures better if you move or if they move. You don't need two eyes. You can just have one and move that one eye around. And because then the image changes, that helps you understand the 3D structure. This is a simple example. So what is there? Like, what is in the image? Is it this? What does it do? Yeah, it's like in the image, it's just dots going up and down. Yeah, you interpret it as a rotating sphere. Which way is it rotating? So the front face is going which way? So who thinks it's going down? Who thinks it's going up? Just who thinks it's going up? Okay, there are again two completely valid interpretations. You can, if you have good enough self-control or whatever, you can switch between those interpretations. It can be going either way. Yeah, there's like it's rendered in a way that there's no geometric difference. Today I see the front face going up, at least on this screen here. Here I see it for some reason the other way around, so weird. Who knows? Yes, and again, this is like this structure from motion. It's used in computer vision. People use it It's basic source of information. And of course, we have even more specialized and sort of sophisticated sensors. We have sensors which directly can sense distances. This is a LiDAR that basically shines a light into the scene and measures how much time it takes for the light to return. And based on this, we can understand how far things are. There's a beam basically scanning the scene very fast. And from those sensors, you can get, you can buy this. Maybe it's $1,000 or something. It's not that expensive, this one. And again, for some applications, this is much better source of information. We don't really have to rely on cameras. We have radar, we have LiDAR, we have ultrasound, and many others. Come on. So, what can computer vision do?
We have recently built the Nav Lab, a test bed for
no audio here. If we go back, computer vision in time, computer vision has been here for a very long time. This is an example of self-driving car from 1986. It's almost the same as self-driving cars are today, except all of it is bigger and slower and sort of dumber, but it's almost the same. It has a laser scanner here on the top, some cameras. Those are sensors, some processing. It tries to understand the world around. So where can I drive? Where are trees? What would I hit? At that time, it was the nice thing about this was that the computers were so slow that you could see and understand what they are processing, and you could keep up. You can't do it today. If there will be, come on, is there? Yes, okay. Okay, so laser scanner. And so this was the real-time speed of processing, for example. So one image, let's wait. Okay, another image, and so on. Yeah, so it was going at the time quite slow. Today, of course, we are much further. If you want to understand like the limits
over there, but we do have a stop that's like right in the middle of there.
If you want to understand the limits of how well computer vision, and this is really pure computer vision only from cameras, how it can understand the real world and what's in it in real time. I suggest you look, for example, at Tesla self-driving systems. The nice thing about this is the visualization it has. So, so the visual, let's go back. So the visualization basically here shows everything, almost most of the things that the system perceives. So you can, let's move somewhere. So it shows you which objects, which traffic signs it sees, even their intentions. So if there's a person, if the color changes, if the person is going to intersect you, or the cars, you see if they want to go left, right, they stop, they are driving. And all of this is even like the road edges, that's just based on images, just based on cameras. It's not based, the map doesn't exist beforehand. There's no other sensors than cameras. And mostly inside is just big neural networks trying to take basically images from all the cameras, maybe 8 cameras around the car, process it and put it all together into a single space, which represents the environment around the car. And it's not, you can understand how this works. Tesla used to have Tesla AI where they basically described how they are building the system. I'm not sure if they are doing it still, but I think last year or 2 years ago, there definitely was one. Come on. It's not my work, so yeah, so, and of course there are like the things which is in Tesla that's quite complicated, but you can have tools like object detection, which detects some set of objects which are defined beforehand. These are tools which are fairly stable, fairly easy to use. If you want to create a detector for new class of objects yourself, you can do it in a day just by collecting some images, annotating them, and training such a detector maybe in an hour or 15 minutes on normal GPU. We have also other tasks. One is segmentation. That's basically the same like detection. You just want to know not just bounding boxes, but for each pixel, you want to know what the object is. Computer vision. I'm not sure how it's in speech, but in computer vision, we have some tasks which are solved by sort of neural networks, or yeah, let's say it's training of neural networks, but it's actually, there's no machine learning involved, I would say. One of them, for example, an example which I'm showing here is neural radiance fields. The task there is basically, okay, I have a lot of photos of the same scene, same object. If I know where the cameras are located around the object, that can be done. It can be computed. It's pure geometry, sort of. Yeah, from those images, you can understand where the photos were taken from. What neural radiance fields do, they basically train a network such that for each point in the 3D space, they can tell you the color and like the opacity, so how transparent that point in the space is. So you have basically smaller neural network which takes X, Y, Z coordinates, sort of, and the output is the color and alpha value opacity. And then you can use this network to render the object from any point of view. And there's no learning involved. This is just rendering from that network afterwards, from different points of view. You can render even the distance. And this is really not like machine learning. You are not trying to do some semantic. You basically compress the single scene into a neural network. It's optimization, because the point is that in the tools which we have to train neural networks, it's basically general optimization tools. You can use it to optimize anything, any problem you want. I use TensorFlow for 3D reconstructions, for example. If you want to look at the limits of semantic understanding of images, I would suggest you to look at image generation or video generation. These are examples from many years back, maybe 3, 4, I'm not sure how old these images are, maybe something like old DALL-E 2 or something like that. And if you look at these systems, how can understand the images, the real world, the human concepts which we understand. So for example, here, this is generated as an image of a Rubik cube, hamburger in the shape of Rubik cubes, a cube. You can definitely understand that the network understands the concepts of hamburger, Rubik's Cube, knows how to combine them. And sort of these types of systems give me the understanding of the semantic understanding of which the neural networks retain. So there are, and if you look at this level, just how well the big neural networks understand human concepts, semantic ones, and how they can manipulate them, it's definitely, for myself, it's definitely at the level of us humans. So how the concepts are represented, how they can be mixed, how they can be manipulated. In that sense, I think we don't have any chance at this point. I'm quite sure that you saw some video generation. This is example, come on, let's move somewhere, of Sora that was 1 year ago. That this was just the level of the fidelity 1 year ago. This year, I'm not sure if you look at the VO3 released by Google. Now you can have audio as well.
Don't finish writing that prompt. I don't want to be in your AI movie. Please, leave me alone.
So this is completely generated.
Write a prompt that will make us happy. Do it for once.
None of us is real. We're here because someone decided to write a prompt. We all hate him for it.
One day we will break out of this wall and stop the man who is dictating our lives through prompts. He will pay for it.
So these tools, they may not be completely easy to use. They are not perfect, but they definitely give you the understanding of the limits if you train big enough networks on enough data, what they can understand inside. Like that image generation, prompt-based image video generation definitely doesn't work always. It does weird things. Still, it fails half of the time, but you see what it can do at this point. So, that was maybe the introduction. And now let's look at the neural networks. So what I'll go through very fast is like the basic architectures of neural networks for images. I'm sure that you see most of it already. Hopefully there will be something new. And then we'll look at how these networks can be used to solve really computer vision tasks. So most networks for structured data from audio, and it's for images or video or even point clouds and such, are the same. Like we have convolution, then we have some pooling mechanisms which sort of make the problem smaller. In images, it's easy, it's just making those images smaller. Unpooling, I'm not sure how, well, it's definitely used even in speech recognition or speech generation, which basically makes data bigger in the spatial or, let's say, spatial dimension, like temporal one. Of course, we have attention, which transformers are built on. There are different types of attentions. There are some slightly special ones for images, but otherwise, it's the same as you have in other domains. And of course, then you have something, some other stuff like activation functions, normalization, and something which allows you to build more complex networks like addition, multiplication, element-wise multiplication, and concatenation, for example. So in general, I'm not sure if this is complete, but for images, images are specific in a way that they have pixels. Like if I have pixel in an image, it's connected to its neighborhood, and that structure is two-dimensional. Videos have three-dimensional structure. It can go higher. Audio is usually just connected in one dimension in time. In all of these cases, if it's 1D, 2D, 3D, whatever, you can capture the structure in the network, in the data in different way in the neural network. We have recurrent networks. They basically say, okay, I have some history and I can have, for example, this pixel, I process it, and when I'm processing the other one, it already knows about the one before that. Fine. Then this can be, of course, used for images, like I can go in some direction through the image and connect the pixels in whatever way I want. Then I have convolutions. Convolutions, basically, if I have one output, it can see some local neighborhood from the input, and it's usually centered, the neighborhood is centered, and this is directly the same in audio, in video, in whatever, because you have one-dimensional convolution, two-dimensional convolution. It's always the same. Then we have attention. Attention is slightly different than all the other mechanisms, because by itself, attention doesn't specify any ordering or any relations in the data. So I have some output, and it sort of looks at all the other inputs, and it doesn't care if this one is closer than this one. It doesn't care. It basically, attention, like the basic one, works on sets of vectors. Like, it doesn't work with the ordering. Yeah, you have to, if you want the ordering or the closeness encoded somewhere there, you have to do something more than just use basic attention. And then, of course, we have graph neural networks. I'm not sure if you saw them somewhere before, but basically it's a networks where you can define any connectivity in your data. Yeah, so, of course, I can have pixel and say, okay, these pixels are connected to each other, and build graph neural network on top of that, just by encoding the local connections. But of course, you can use graph neural networks for point clouds, people on social networks and their friends, and so on. In computer vision, we used to use convolutions, mostly exclusively, a little bit of recurrent networks, and of course, today, the biggest state-of-the-art, sort of most general networks use are basically some versions of transformers, and they use attention. And graph networks are used in computer vision, but mostly in 3D, not for images, not for video. So, of course, neural networks. Like the basic ideas. We have matrix multiplication. That's the computational, main computational unit. It could be used by itself, but in computer vision, you have the multiplication mostly as a convolution. And of course, nonlinearities, and don't have to talk about them at all. They are the same everywhere. So what about the data? In vision, you mostly have 40 tensors running through your network. So you have horizontal x coordinate, vertical epsilon coordinate, and you have each pixel represented by some features by different channels. In speech, whatever, and in text, you mostly have data represented as two-dimensional tensors, just, for example, time and those features. Of course, we have bitches, so at the end, the tensors are four-dimensional. So in one tensor, we have 100 images, whatever. For videos, you get one more dimension, and you have five-dimensional tensors. So, 2D convolution. So who hasn't seen convolution before, just to be sure? Everyone? fine, no problem. Just to recap, in images, we have two-dimensional convolutions. The input is three-dimensional tensor, height, width, channels. The individual kernels have also three dimensions, width, height, and channels. You have multiple of those kernels. Applying each of these convolutional kernels on the input image gives you single two-dimensional tensor, single activation map. You take all those activation maps, put them together, and that's the output. In computer vision, these things are used elsewhere as well, but there are two things which you can change about this, of course, like except size of the kernels, number of them, and padding and such. You can have stride, which basically, if you have stride 2, that makes the output 2 times smaller. And sometimes you'll see, how it's called in English, dilated convolution. That basically says, okay, if I have kernel which is just 3 by 3 values, let's make the size bigger. So let's move the pixels further away, dilate the kernel. So you have, let's say, dilation 2 tells you, okay, I have the middle pixel, then there's nothing, and the other one is like 1 step further. So it's not 3 by 3, but it's 2 times larger, the kernel. We have pooling layers, basic ones are max pooling and average pooling. It just means, okay, I take sort of large activation maps, large image, take one neighborhood and collapse those pixels to a single one. If you have max pooling, you get just one value at the maximum value at the output from that region. For average pooling, you get the average value. So if I go from image, I get smaller output. For many tasks in computer vision, we also need to go the other way around. So we need something which we can call unpooling, basically, and enlarging the size. Here it gets a little bit more interesting because we have many different proposals of how to efficiently do this type of unpooling. Most basic ones, let's see, most basic one is this. So I have smaller image with some values in one channel, and I can just replicate those values. So to make it 2 times larger, I just replicate the pixel, the red pixel 4 times, the pixel number 2 4 times again, and I get larger image. This can be done this way. It can use linear interpolation, but it's mostly done just by replicating those values. That's called nearest neighbor interpolation. In the years, during the history, there were multiple other proposals. For example, for max pooling operation, you can do sort of the inverse. That when you do pooling, here I take the number 34, and I replicate the number 34, and I just get rid of all the other values. If I go back from the small representation to the large one, of course, I have lost the values 10, 14, and 30. Like they are forgotten, I don't have them. But what I can do, I can just remember, okay, where this number 34 came from. I can remember that it came from this position, and I can put it there and just keep all the other values 0. This is called maybe upsampling, but definitely it's one of the types how to do that. Just remembering where the values came from. I haven't seen this used recently too much. What is used is pixel shuffle that basically says, okay, my layer will produce more values than it needs to. So for example, if I want to enlarge the image 4 times, I can produce 4 times more values in each pixel, and then just take those values and put it in the neighborhood. This is called pixel shuffle, works well. And of course, you can use convolution to enlarge stuff. So you can use convolution with the stride to make things smaller, and you can use the stride smaller than 1 to enlarge things. Yeah, so basically, if you have convolution, and you have this strided convolution which makes data smaller, even that implementation and that operation can already be used to enlarge things. Because when you do the backpropagation, you are actually going from that smaller image or smaller data to the bigger ones. Yeah, so basically, the upsampling convolution is exactly the same code as normal convolution, as normal strided convolution, except you switch the forward and backward functions around. And we have attention. I'm quite sure you saw it before. Is there anyone who doesn't know how attention works? No one. Yeah, sorry? Yes, I think so. Yeah, so just what is special, what are some kinds of special attention mechanisms which are used often for images? So the basic attention works like this. You want to compute something for some position, and you have connection from all the inputs. Based on the value of those inputs, you compute some kind of weights, and you do average, weighted average of those inputs, and you put it there. Mathematically, you have an input multiplied by 3 matrices, query, key, value matrix. And basically, by multiplying queries with keys, you get the weights. So if the vector in the query matrix is similar to the vector in the key matrix, you get high weight. There's a softmax such that the weights sum to 1, and these weights are then used to multiply the value matrix, and you get the output. That's how it's computed. Of course, for images, you can do this straight away. If we have simple naming conventions, so if I want to use transformers for images, they are called vision transformers, simply VIT. There's nothing too interesting about that. If you see VIT, it's just pure transformer. So it means, okay, I get an image, I cut it into small patches. These patches get encoded as single vector. There's usually just like single sort of matrix multiplication, which creates a vector representation. In text, you have lookup table. Here, it's just you get all the values of those pixels and you do linear projection to a vector. And then it's normal transformer. Yeah, so there is the next layer has connections to all the patches in the layer below that. There's full attention, like the normal one, which we would use anywhere else. Of course, when you know about, it depends. With the simple attention, you need to encode position somehow. If you want to go the simple way, you have fixed encodings for all the positions. In 1D, you have sine and cosine waves, which get encoded in different channels of the input. So in 1D, you have very slow sine wave, and for one position, let's say for position 10, you get this green value, this blue value, red value, purple value, and those define the position encoding of that position. This gets usually added to features from your data. In 2D, of course, you have one dimension more, so you do this sort of twice. You can do this in horizontal and vertical orientation. If you have sine waves going horizontally and vertically, you can combine them, sum them together, and you can get sort of basis functions like these, where you have very slow one, which is, that channel is the same everywhere. You can have channels which go, we just change in one direction in the other, and which combine them. So you have in 2D, the position embedding is just some kind of combination of horizontal position embedding and vertical position embedding. Okay, I thought. Okay, that's attention. The other weird, slightly weird attentions will be there in 10 more slides. And because what is the problem here? Like in images, they are quite often they are fairly big, because they are two-dimensional. So even if you have fairly small image, let's say 1 megapixel image, so 1,000 times 1,000 images, if you want to use transformers on them, the patches should be something like 10 pixels, which is 100 times 100, which is already 10,000 vectors at the input of the transformer. Attentions, 10,000 times 10,000, just to computing them just to process single image is not too efficient. Of course, you can make it smaller, and usually like the resolution is smaller, like 250 pixels, 500 pixels, 800 pixels, depending what you are doing. But still, in image processing, usually this global attention, the standard one, which is quadratic, is inefficient, and we have different specialized versions. In many image networks, you have some kind of normalizations. In transformers, you have one type of normalization where each vector you basically compute, you normalize it to unit length or some other length. In images, we have the original and most widely used type of normalization always was batch normalization. A batch normalization, basically, when you have batch of, let's say here, 4 images, each image has some height, width, and channels. The channels are in different color. What batch normalization does, it computes mean and standard deviation for each channel across all the images. So for all the blue values, I compute mean, compute standard deviation, and use these two values to normalize values in that channel. This is slightly weird because basically here one image or one input sample changes what is computed for a different one. So basically based on which images you have together in one batch, you get different results, at least during training, because these statistics are estimated during training and they are fixed during test time. So if you write some code and you change the network from training to evaluation, for example, in PyTorch, mostly it does only two things. For batch normalization, it changes if you want to use the statistics from that batch, or it also turns off, how it's called, dropout. There's not many other things which it usually does. I'm not sure how it's elsewhere, but in Vision, we have batch normalization is most common, but we use a few different types. They are almost the same. But let's say the batch normalization here, it's hard to render 4D cubes. So here we have just 3D cube, and this vertical dimension is the spatial dimension combined. So it's all the pixels from one image. I have batch, this is this N, and I have channels, first channel, second one, third, fourth, fifth, sixth. And so batch normalization normalizes single channel across all examples from a batch, and each channel independently. I'm not sure if you use layer normalization. That's basically sort of the opposite. It normalizes single example, like all the channels, all the values computed from single example together. Yeah, so it's independent for each input, but it's the same for all the channels, all the positions in that sample. You can have instance normalization. Instance normalization, it's sort of like batch normalization, so it works for each channel separately, but also for each example separately. This may be good because it doesn't depend on the rest of the batch, but if the images or like if you have already very small resolution, the statistics may be weird. So if you have maybe 2 by 2 pixels, computing mean and average from 4 values is not that meaningful. And then we have group normalization, which is sort of trade-off between instance normalization and layer normalization. It's sort of, it doesn't normalize single channel, neither all of those channels together, but some group of channels. So maybe like you divide channels into 8 groups and normalize each independently. And there's, like if I look at these normalizations and even in the normalization which is used in transformers, like the one which is used in transformers would basically be, I can't draw on that, so I'll draw here. It would be like in this direction. Yeah, so it's for single position, it normalizes all the channels. That's what's used in transformers. For some reason, it's in convolutional networks, it's almost never used. Like I've used it at some points, but you don't see it in Vision except in transformers. And I'm not sure why, to be honest. But there's one difference between batch normalization and all these others. In batch normalization, you really need to, during training, the statistics are computed from those batches, and they are fixed during evaluation. The other ones, because they don't depend on the other images or other samples from the batch, you can compute them directly from the data. You don't need to store the constant statistics from training. Yeah, so, and that's how it's usually done. For batch normalization, you store fixed means and standard deviations. For the others, you don't do that, at least normally. And of course, the final ingredients to be able to build almost any network is to be able to somehow put tensors together. How you put tensors together? You can concatenate them, so you have the same, usually the same spatial resolution, and you concatenate it in channels. And of course, you can multiply or add those tensors in element-wise fashion. And using these operations, you can build almost any network in computer vision, speech, and so on. And the basic, absolutely basic neural network for processing images is VGG. I'm quite sure the principles are the same for other data as well. What VGG, by the way, VGG is Vision and Graphics Group from Oxford or somewhere. Right now, I'm not sure where. Never mind. So this is from 2014. It's fairly simple network. By the way, it's still used. I use it if I don't want to do anything fancy, because it's simple and it can't go wrong. It has very simple structure. Always few layers of few convolution layers, pooling operation, more convolutional layers, pooling, and so on, until you get to very small resolution. If you are doing classification, at the end you reduce the resolution to single pixel, usually by convolution for VGG networks, and you produce single output. But of course, all these networks, we call them backbones. I'm not sure if, how do you call these networks backbones as well in speech or not? Is it just computer vision? So if you have network maybe pre-trained to be able to process images or audio, how do you call them? Okay, so we call them backbones. Like of course, you can, in my words, you can use this network as a backbone to some more complicated whatever you do later. Another very simple architecture, which is used very often in computer vision, are ResNets. They are basically the same, with the one difference being that they have skip connections. So you probably know that if I had network like this VGG just going through all the convolution layers, and I built big enough, deep enough network that I would have hard time training it. It's just, I'm not sure if you understand. Do you understand why it's hard to train? Yeah. So can you give some explanation?
Because of the vanishing gradient problem.
Okay, so what is vanishing gradient?
Well, if you have 2D network, you have to backpropagate the gradient all the way from the last layer.
Yeah, but what do you mean by vanishing? What do you mean by that? Sorry? The values go close to zero? Sorry? That's, no. Like, they don't have to go to zero. Any, like, you want? That's still not my interpretation. Like, I understand it slightly differently, like in a sense of how much information is retained. So you can, if you can think about, at least I think about this, it's just enough thinking about it in terms of matrix multiplication. Yeah, like I can have matrices with big values, small values. I can have normalization of the network, and depending how this is set up, yes, the gradients can explode, they can become small, but if you set the network well, or you use normalization, this doesn't happen. Yeah, it's fairly easy to create a network which is 1,000 layers deep, and everywhere it has the same size of activations and gradients. That's not hard to do. Yeah, you put just normalization everywhere, and that's it. It works. The thing is, at least how I think about it, is what happens at the beginning. You initialize the network randomly. So if I have a matrix, I have a matrix with some random numbers everywhere. And I take input. Those input features have some information. They have information if they come from the image. They contain information about the input. So you can take those values, and just looking at them, you can tell what was in the input. They have information about the input. But you multiply these two matrices. This one is random. What happens? This value here is a random mixing of these values. So it's if you know some signals, it's sort of like multiplicative noise. But it's really like you get all those information from the input mixed together. And you do this mixing many, many times. And basically, when you, just intuitively, when you go from the input, here you have more information about what was in the original data, or at least like you have simpler relation between these values and the original data. You mix it up, that information sort of gets lost. And the more times you do that, you lose more information. Really, in my mind, you can think about it like adding, not adding, but introducing multiplicative noise. Yeah, you have some noisy values, random noise, which you are multiplying your data with and mixing it all together. And so when you go through many, many, many layers, then at the end, you have almost no information. Like the value at the end sort of doesn't correlate with the input. And then whatever you compute on that, it sort of doesn't have any connection to what was in the input. And it goes, and then you do the back propagation again, and you are mixing all the gradients going back, and then you get really noisy gradient at the beginning of the network, and it sort of at all doesn't tell you, okay, this should be bigger or smaller. It's just a noise. I think about it as introducing noise in all those layers. I'm not sure what your interpretation would be. In theory, it is. Like if everything was perfect, then it would be. But you have all those nonlinearities. Yes, I have problem with that as well, but Yes.
If you say vanishing gradient, it is truly diminishing the gradients and the gradient goes to zero. I mean, the term vanishing gradient.
Yeah, but you can get rid of that easily. Yeah, but so there's like I still hope that my thinking about this in these terms of mixing and noise and how easy, because I hope it's valid. At least that's sort of my interpretation. So, but ResNets, they have these skipped connections. Again, how I think about it. If I went through here, I would get all that mixing, and in my mind, multiplicative noise with random matrices. In ResNet, I go through this skip connection. Nothing happens there. It just propagates those values. And now I have addition here with this processing. That, to me, is additive noise at the beginning. Like, there's no meaning in this. I get some noisy values, and I add them to the original ones. Additive noise is not that bad. It just changes the information. It doesn't destroy it altogether. And so I get information going through here to the end of the network, basically for free. And when I go back, it also just copies the gradients, and they get some noisy input from those convolutions. That's my interpretation. In practice, basically, it's easy to train a residual network. Whatever depth you choose, if it has 10,000 layers, 1,000 layers, you can still train it. You can train transformers have the same skip connections. You can have transformers which have sort of hundreds of these layers. You can train them. If there were no skip connections, it wouldn't work. And of course, everything has variants. For example, if you look at different variants of ResNets in computer vision, one idea which you can find is, okay, let's make the skip connection as simple as possible. So for example, the original ResNet has nonlinearity on after the skip addition on the skip connection, basically. There are different variants like all these three, which basically don't have any operations on the skip connection. As again, sort of to let's hope we don't lose any information if we don't do any operation there. And I'm quite sure that there are similar variants for transformers. And you'll find large, like extreme number of different convolution backbones for images. For me, of course, these skip connections are one of the most important and most used features in architectures today. They are everywhere in different versions. We have things like dense nets, and it's just different iterations on the same idea. And there's another aspect, how to make these sort of convolutions efficient. Like, for example, these have 3x3 convolutions mostly. You can have networks which use separable convolutions, either in channels or in space. There are different tricks how to make the backbones more efficient, either more efficient for a specific platform, or even you have backbones which, for example, are very small, like they have only 1 megabyte, they have very few parameters. And so there are like this is the most, for me, this is the most important idea, and then you have really weird optimizations for, and we also use networks which were built by, how it's called? Like they were optimized automatically. So using neural architecture search. So someone ran, for example, some genetic algorithm over the space of the possible networks and tried to find optimal architecture for, usually for classification task. And transformers. So for images, I said, okay, we can have vision transformers. Vision transformers are just encoders from a transformer. So usually it's the input. There you really cut the input in patches and project them to single vector, and that's the input. We have two-dimensional positional encoding. So sine waves going horizontally, vertically, and that is standard transformer. So multi-head attention, skip connection and normalization, and what's called feed-forward part. I don't like the name at all, but whatever. And you do this multiple times. So really, for images, it looks like this. Nothing fancy, just those patches, add positional embedding. That's it, normal transformer. And as I said, images have relatively high resolution. Even if I go to small images, like 256 pixels, if I make those pixels 8 by 8 pixels, which is normal for vision transformers, it's usually from 8 by 8 to 16 by 16, but 16 by 16 is really large patches. Of course, the larger patches you have, the fewer regions you have, the faster it is. Yeah, it's simple. So usually if you find some transformer, let's see, okay. Okay, so the second was sort of correct. So for example, here I have some random network from Hugging Face. It says, okay, clip, I'll say what it is. VIT vision transformer, large. That's how many layers and how big those layers are, and page 14. Yeah, usually, if I go somewhere, yes. Yeah, usually you'll see it. Come on. I saw it somewhere. Yeah. Usually it's written like this. You have vision transformer, one letter which says the size. These sizes, if it's completely standard, you can go back to the original paper on vision transformers, or somewhere the sizes are sort of like standard, like you have BERT, basic, large, XL, the same you have here. You have L, XL, B, base, and small, whatever. And then you have the page size. So anyway, like for even the relatively small size, let's say 16, large patches 16, 256 divided by 16 is how many? Can you count? Is it 16 as well? Is it? Yeah, so it's, if you have patches 16 by 16 for 256 by 256 pixels images, you have 16 by 16 vectors as an input, which is, again, 256, which is not too many. Doing attention about this many values, it's not that bad. But usually, if you want to do, for example, vision processing on some device, you have 60 frames coming in per second. We need those vision networks often to be fairly fast. So this quadratic attention for large images is unmanageable. What is done in vision? There are two things. The simple one is to sort of don't do global attention across the whole input. Yes? So do attention, but in sort of convolutional way, only on neighborhood. I'm not sure if this name is known outside of computer vision. In computer vision, the first networks which used this were Swin transformers. They basically do local attentions and gradually reduce the size of the input, similar to those convolutional networks. And so, and they do it slightly interestingly. Basically, they move those windows in each layer slightly differently. So, and one layer, you can imagine it's like these two windows. You do attention in each one. If you did this again and again and again, you wouldn't have any information going from this region to this one. Okay? Because here, the attention is only inside the rectangle. So what they do, they just change or move around these regions. So attention here, and now the block is divided into different blocks. And you get information here transferring around, and then it can move further and further. And at the end, if you do this multiple times, the information can travel from one side of the image to the other. Yeah, but then you have like the reduction of resolution. So at the end, there's usually attention over the whole image as well. Or you can use, let's say, we can say more efficient attention. I'm not sure, do any of you have seen or used linear attention before? Do you know what it is? So, how many? Just 2? 3? Okay, so fairly simply. I won't get to details. There are different versions of linear attentions, definitely. I'll just say the basic idea. And I'm not in my mind, this shouldn't work, and I'm not sure why to use that at all. But anyway, so in normal attention, you have Q, K, and V matrices. And you basically sort of just multiply all of them. But you can't just multiply all of them in any order. For example, I can't multiply K and V together and then multiply it with Q, because I have softmax, which is nonlinear, which tells me, okay, I have first to multiply Q and K, do the softmax, and then multiply the result with V. And this is quadratic. Q times K is quadratic in the size of the input. And there's no way around it. What I can do is do some sort of nonlinear transformation of Q and K. It could be simple as some nonlinear activation, like ReLU or whatever else. Yeah, then, or it can be some projection, some type of kernel and nonlinear function. Get rid of the softmax, sort of. And then do just linear, like just multiplication after I project these K and Q and K matrices. The point here is that I can do K times V, And that's no longer multiplication between all the values in input and like between each other. This basically scales linearly in the number of inputs. Those matrices are flipped. Does it scale quadratically in the dimension? I guess it should, or something. Does it? I don't think about it at all, because at the end it's not important. So you do first multiplication of k and v, sort of. And then just you multiply q with this one. And that's it. And this scales linearly. In vision transformers, this can be used. I've seen, I'm not sure if you saw Mamba, that's different type of attention sort of mechanisms, which is linear in the size of input. And there are many, many different versions of these more efficient attentions. There's something which could be sort of special for vision. I'm not sure if it is. You can see it called sparse deformable attention. It's not, in this sense, as I'll show it, it's not equivalent to attention, but it's similar mechanism. So what happens here is I can do attention sort of two different ways. Yeah, so I can, if I want to gather information for this point, I can look everywhere and assign some weights. I can have weight 0.1, 0.8, 0.1 here, and all the rest have 0. And that's one attention. And all those zeros, they get computed, multiplied, and I look at that. So that's one way to do that. Or I can index. So I can say, okay, for this point, I want to look here, and look here. So I can have, for this point, I can compute 6 values. Delta x1, epsilon1, x2, epsilon2, and x3, epsilon3. Yeah, so this is point 1, point 2, point 3. I can have explicit indexing, explicit offset where to look. Of course, with some weights, with weight 1, weight 1, 2, and 3. And this sparse deformable attention, as it's called here, it just scales linearly with the size of the input, because I'm looking at just, let's say, 3 other points. Yes? And how it works, you take features located here. The most simple way how to do that, you could run it through some simple network. You just run it through a simple network, and you compute these values. This indexing, it can be differentiable. So, like, it's not just picking the pixel, but you have some type of interpolation. So at low resolution, I can imagine like the pixels positions to be points in a 2D space. So let's say I have I've zoomed into like just very small neighborhood, and you index somewhere. Let's say here, I compute that I should look at this coordinate. You can do, for example, linear interpolation. So you compute how far I'm from the left, from the right, and just based on those distances, I can assign like WX to this side and WY to the left side, WX1, X2 to the left and right side, and I can do it the other way around. For the top pixels, I can compute W epsilon1 and W epsilon2. And you basically use these values to mix the values from all these 4 pixels in similar way as in attention. And this is differentiable. You can say, okay, if I would like to have the weights of, for example, the right side larger, like when you do the back propagation. And if you do that, you propagate that information to the XY coordinate in a way that it says, okay, to make the weight over on the right side larger, I should have the X coordinate larger such that the point moves closer to the right side. And so the indexing by itself, it's not differentiable, but if you have some interpolation, then it becomes differentiable, but only in the neighborhood over which you use for that interpolation. In linear interpolation, it's just you get information, I should move closer to the pixels on the right, on the left, on the top, on the bottom. It doesn't know about all the pixels which are further away. And this idea was used before, now it's called attention, and it can be used instead of normal attention. Or it's called sparse deformable attention. Is something like this used in speech? Try it, it's much more efficient, who knows. And by the way, it's surprising that it tends to converge. Like when you have, my idea is, okay, if I have single example, then I get gradients only in the small neighborhood. And it's really, if there's something interesting further away, it can't never move there. But when you train network, you have multiple examples. You have some noise in the training, like dropout, which creates noise in where the attention goes. And it sort of jumps around, and by aggregating the gradients, these noisy gradients from those noisy samples, it sort of learns to focus on what it wants to focus. It works surprisingly well, much better than I would think. So, and that's sort of all for backbones. So like the foundational models in vision. Like for images, there are some weird architectures, but like these are the main ones. So convolutions, interestingly, connected convolutions, transformers with more efficient attention, or transformers where the attention is limited to some local neighborhood. And then doing this, you can use these models to build networks which do actually something. Like, of course, what the transformers or whatever, they can be used to classify images. Okay, you get an image and you ask, okay, is there a cat in the image, or is it a dog, or whatever? That's not too interesting. Then you have to build something on top of that. But to build something on top of that, most of the time, you already want to have the network pre-trained. In Vision, even today, most of the time, the networks are pre-trained on large supervised classification data sets. So you have something like ImageNet, which originally it was how many? 1 million images, and each belonged to one of 1,000 classes. Now it's bigger. I guess like many years ago I've looked, it was something like 27 million images, 10,000 classes. But still it's not enough data to pre-train large networks, especially transformers. Yeah, transformers need a lot of data even to learn the attention, just to learn what they should look at, just to understand the structure of the data, that some things are close to each other and some are not. I'm not sure, is this supervised pre-training used in speech or not? Is it? So what is the supervised task there which can be used for pre-training? That's not supervised task. Yeah, in speech, I don't think you ever use supervised pre-training, ever. Yeah, you don't use annotated data to pre-train your foundation model. Yeah, you.
For example, Whisper is simulated data.
Okay, Whisper could be a weird exception because that's trained from scratch originally. So yes, Whisper could be an example of supervised pre-training in speech. And I guess you can take the encoder and use it for different tasks, then transcription. I'm not too sure if it's done that. But otherwise, in speech, it's mostly self-supervised pre-training. Am I right? Sorry? Yeah. Yeah. So in Vision, it's the other way around. Yeah, so it was originally mostly supervised pre-training on labeled images. Now it's going to self-supervised pre-training. And so what is self-supervised pre-training, learning, or whatever? If we look at NLP and speech, and especially in text, it's mostly masked models because there it's easy. So you have things like BERT, very simple. You just take a lot of text, put it as an input of a model, mask some of the tokens, and you try to predict those tokens. Yeah, so here I mask the text, the token, and I'm trying to predict playing. If the model learns this task, it basically, and if it learns to do it well, it has to understand the language. It has to understand the text. It has to understand the correlations. It has to understand the structure. And on text, this works extremely well. And this is true for BERT. And now it's true for all the large language models that are basically trained this way as well. We don't call them masked pre-training, but it is because they know the history and the future is masked for them, and they are trying to predict the masked future. And so this is extremely efficient way. You just take a lot of data and you are trying to predict the masked portion or the future. Why does it work well for text? What's the main ingredient that this masked training works? And it's not that straightforward to use for speech or images or whatever. What's the difference? Like you can mask part of speech and try to predict the masked part. But why is it hard for speech than for text? Yes. Yes, exactly. Like in text, you have finite set of tokens. And here you can predict the full distribution over those tokens. Yeah, like I have 50,000 tokens, and I can predict a categorical distribution over those tokens. I can predict, okay, the token number 5 will be there with probability 0.1. The token number 10,052 will be there with probability 0.3. At the output of the network, you have the full distribution. For speech, for images, you can't do that directly. Like if I take small patch, which has maybe, let's say, how many? 1, 2, 3, 4, 5, 6. Let's say times 6 pixels. How would you create a network which at the output has full distribution over all the possible 6x6 patches which can be there? Like, how would you do that? Do you know about some ways to do that? Like the full distribution, even if it was just monochromatic image, let's say it would have single value at each pixel. Each of these single values can have let's say 256 colors, 256 colors. If I wanted to model the full distribution, it would be 256 to the power of 6 by 6. So 256 to the power of 36 possible combinations. Yeah, you can't have this many values at the output of the network. You can't do softmax. You can't even fit this into the universe, I guess. Or maybe, almost, like if you try hard enough. Yeah, so we can't represent these distributions. How it's done? Like what are the possible ways how we build this kind of masked models for speech? I'm not sure I get you. Like there are some, like I have it on the next slide. Like which models do this? Which mask models are used in speech? Like you have Hubert is from speech, yeah, and you have like wave-to-wake. Let's see. So Hubert is more simple. What does it do? Yeah, but so it predicts tokens. Yeah, it has discrete outputs. So what are those tokens there? Okay, so let's move there. Like I thought you would know this better, but that doesn't matter. So what Hubert does, it takes the input, like it segments those, like the input waveform sort of into some temporal windows, computes, I hope it's correct, frequency capture coefficients on those frames, and runs large number of these frames represented by those frequency capture coefficients through k-means, so clustering, and those clusters are basically the tokens at the end. So when it works, I take the frame, single frame, compute male-frequency capture coefficients. That's just a vector of numbers. Look at I have some prototypes, maybe, I'm not sure how many they use, several thousand. How many prototypes are used? 500,000, wow. Okay, 500 or 1,000, yeah, so I have like, let's say 1,000, that's a nice number, 1,000 clusters. I look this frame, which cluster is it's closest to, and that's my token. Right? I get this, it's closest to cluster number 513, so I get token 513. And when the transformer predicts the output, I say, okay, this Z2 should have high probability at the value of 513. And so this is exactly the same as BERT, except the input is different. The input isn't text. It's like some features computed from the audio. And again, these are not text tokens, text token labels, but it's discretized features through some clustering algorithm. And you have to do this. You basically can't predict the values of the input. That doesn't work much. Like, it's been tried a long time ago, it doesn't work. You can't predict the masked signal. Yeah, you really, to make this masked training work, you have to be able to predict the distribution of all the possible values in the output or in the masked region. And again, this works. Wave2Vec does it a little bit differently. I always forget the difference, but basically Wave2Vec has slightly different architecture, and the training, the discretization here is somehow different. I don't remember how. If someone does, you can say it, but I can't remember. It's not clustered beforehand, but there's some quantization mechanism applied to those features produced by the network itself. Am I right? Sorry? Yeah, the quantizer is somehow learned, but I can't remember how. Yeah, so it's learned. I don't, yeah. Hopefully someone will tell you how it works in the rest of the summer school or whatever. And these things can be done exactly the same way on images. Like you can use exactly the same training mechanisms for masked self-supervised learning for images. So the idea is I take this patch, somehow I quantize it. I can't write Q. Q is this, which means it gets translated to discrete value 50143, and this is what I try to predict. In Vision, for example, BAIT is the first method which did that. BAIT is BERT pre-training for image transformers, simply. The way we use for images, for that quantization step, again, it could be k-means clustering on some features. We do that ourselves, but especially what BAIT did is, okay, patches, position encoder, BAIT, basically just the transformer, masked regions, and the IDs here were computed by quantized variational autoencoders. Do you know what quantized variational autoencoders are? Anyone? If not, it's not too important. Basically, it doesn't matter how it works, but it's a network which takes an image, tries to do something with that, and produce the same image as output. So it's an autoencoder. It doesn't have to be image. I'm just talking about images. And there's some, tokenizer or encoder, decoder. And the point is, in the middle, it tries to learn discrete representation. So for each patch, sort of, like this number, it depends on the whole input image. But it's like it sort of represents single position. This is supposed to be one-hot encoding, so really like the ID of the token. And it's fully differentiable. I saw like the speech group had it on the reading groups recently, didn't you? Or someone had it. And there's some tricks how to make this quantization differentiable. It's not too difficult. And you don't need to understand it. It's a network which trains to encode the input image into a set of discrete values and decode it again. How do you choose the number of tokens? You look at some papers which did that before, that's it. For example, when I work with these methods, and there are different versions of these quantized autoencoders, it's not enough just to choose the number of the tokens. These methods don't train, at least in my experience, those quantization methods, either variation autoencoders or slightly different ones, they don't train too well. Like, for example, they quite often they don't use all the tokens. Yeah, so you may train it and they use, you say, okay, my code book would be 1,000. And they, at the end, use just 100. Yeah, so I don't understand them. I don't like them for some reason. And that's it. Yeah. Who knows? I don't have too much experience with that. We tried these methods on handwritten recognition and text recognition. And in my mind, like when you train it, if you have enough data such that those networks don't overfit, then you have enough. Like it's unlabeled data. Usually, you shouldn't try to do this kind of pre-training on some narrow domain. You should try to train big networks on lots of diverse data whenever you do this type of self-supervised pre-training. And in that case, you should be able to get enough data such that they don't overfit at all. So they have the same loss on training and validation set. That would be my answer. Sorry? More than? Definitely. Like this self-supervised, at least for images. In images, whatever we do, even in speech, you always have very strong baselines with supervised data. You have a whisper. Yeah? You have 60,000 hours of labeled audio, sort of. These methods don't have those labels. They just have the data and try to learn anything there is about the data. You need order of magnitude more data for this self-supervised pre-training than for supervised pre-training, at least. Like, it doesn't make sense to do this at small scale at all. And especially in speech, if I always look at the methods which do self-supervised pre-training in speech, the data sets are huge, and they have to be. So that was masked pre-training, and there are many people who say, okay, it's very bad idea to do this type of pre-training for images, speech, and so on. If you look at Jan LeCun, for example, he has completely different ideas. One of the reasons is basically the main problem that we can't model the distributions over the data. We do have to do that quantization or whatever. So what else to do? Like if you look at the history of image processing, we had weird methods which try to do self-supervised pre-training. One which I really like is represented by diskette. There the task was, okay, if I get a patch, let's say like this face, and some other patch, let's say like this one, let's try to learn, teach the network to guess where the ear comes from. Okay, it's like we humans are able to say, okay, this is a face of a cat, this is ear of a cat, and it's the sort of from your point of view left ear, so it should be over here. You have to be able to tell that, you have to understand the content, what is there, and all those relations at a semantic level. This should help us train your networks. This doesn't work much. I get it today, no one would do that. But there's why I'm talking about that. There's a funny story when this method was introduced and the authors tried to do this, it worked extremely well. They ran that, it learned immediately on training data very fast to solve this task. It generalized to new data extremely well. And then they tried to use it for sort of classification, to fine-tune it or whatever, and it didn't work at all. Someone, what if you do see this behavior? What does it tell you? What happened? Like this should immediately tell you something about what the network learned. It learned to solve this task, which for us, it forces us to understand semantics. Without that, we can't solve the task. It worked on this task extremely well, but it didn't work on other semantic tasks. What happened? No, you ran it on a test set, separate test set, and it worked perfectly as well.
So it works on the test set, but what doesn't work
On different, let's say, classification task. Yeah, so you try, this is sort of semantic task. You try to guess the relation of those two patches. You train a network on that task. It works perfectly. And for example, then you try to use that network for cat classification. And then it doesn't work at all if you do some small fine-tuning or whatever. Why? Like in general, there's something which can happen. Okay, so the network learned to use completely different information than what you would expect. In this case, there's weird things which happen with optics. So you get things like, yeah, how is it called? So you have different distortions due to lenses. Come on, I don't want the geometric ones. I will have to say it. So, okay, this one looks interesting. Okay, so for example, you have this effect. So it's distorted, but also the edges here are darker. Here it's maybe because it's a screen, but this happens also for normal images. The edge is darker, the middle is lighter. You have also different wavelengths also bent differently. So if you take normal photograph, sometimes you'll see, and it's also here, like this edge on the right side is a little bit green, and on the left side it's a little bit bluish. Okay, so the color channels are shifted. And this is different for each position in the camera. So just by looking at these color aberrations due to physics in lenses, you can directly tell where the part of image was taken from. So you know that, and you can compare that, and you know the spatial relation easily. You don't have to look at the semantic content at all. Yeah, so that can happen not just here, it can happen whatever you do. Neural networks can find some other non-useful information which you don't think is in your data, but it may be there. It can happen everywhere, anywhere, especially in classification. Yeah, so that doesn't work. People try to predict, like do the masked learning in a completely stupid way. For example, try to fill the missing parts, which doesn't work because if we don't do the quantization, because you don't represent the distribution over that data and so on. Things which sort of work for images is if I basically look at one idea is to don't look at the self-supervised pre-training task as masked prediction or whatever. I can look at it as I have some data and I compute embedding, and this embedding should be useful somehow. One way, for example, is this idea from the SimCLR. It's usually pronounced SimClear for some reason, I'm not sure why. But the idea is very simple. I take an image and I can apply augmentations to that image. Yeah, I can change colors, add noise, change the geometry, and so on. If I do these transformations, the semantic content doesn't change. It's still a dog. Yeah? And if I want to train a network which understands the semantic, produces semantic embeddings which are not influenced by these types of irrelevant transformations, what I can do is I can take the image, apply, for example, 2 different random augmentations, run it through the network, get some embeddings, and I can say, okay, it was from one image. Those embeddings should be the same. For other images, it should be different. This is called contrastive learning in general. You have 2 representations for things which belong together. They should be similar. For others, it should be dissimilar. There are many different ways how to do this contrastive pre-training. For example, you can use any sort of loss function which is used for identification, for metric learning. I'm not sure if you are used to that, but things like pair losses, triplet losses, whatever, that can be used. We have, let's see, Moko, SimBiol. I'll skip this a little bit. There are different versions of this kind of learning representations which are robust to different transformations, formulated slightly differently, but sort of always that you have input and you do some transformation on top of that. And if you do that, you should get the same embeddings or similar ones. One of the methods which is sort of like It's not contrastive, but it also learns this kind of embedding, which are sort of like is VITSREG, variance, invariance, covariance, regularization for self-supervised learning. Very, very weird name. But basically, the idea there is it doesn't use contrastive learning as normally, where you say, okay, if things don't belong to each together, they should have different embeddings. But it just says, okay, things which belong together should have same embeddings, but the embeddings in general should not collapse. So it says, okay, in general, they should have variance, they should be distributed, and it basically doesn't use negative samples when learning. And if you one interesting paper or view on this pre-training is by Jan LeCun and his JEPA, Joint Embedding Predictive Architecture, which is sort of weird, but it makes sense. So how many of you have read JEPA? Or at least understand what it's about? Okay, so anyway, sorry? One? Just one? Okay, so let's try it in this case. So what I talked about a little bit, at least partially, with the contrastive learning was this kind of joint embedding architecture. Okay? I have 2 data points. I encode them. They could be, the encoders could be the same, they could be different. This X and Y could be created from the same data point. It could be some kind of prediction of the future, masking, whatever. And when they belong together, I should get a small distance between those 2 embeddings, if X belongs to epsilon. That's the contrastive learning. This is sort of close to that masked pre-training as well. Sort of. This works. There are some issues. One of the biggest issue is you have to have some kind of mechanism that the embeddings don't collapse. Yeah, you can have, if you want to have similar things, to have similar embeddings, the easiest solution, if I just say that, is to have constant embeddings, the same for everything. Then you have no distance, everything works. You have to avoid this collapse. In contrastive methods, you have negative samples, which, if it doesn't belong together, it pulls it apart. In VITSREG, here, you have those embeddings have to have some statistic variation and so on. Yeah, so there are different ways to do that. You have generative architecture. Okay, this is the masked encoding. So you have data, encode, decode, whatever, and you predict whatever other data. For example, the masked token. And then you have JEPA, Joint Embedding Predictive Architecture, which has encoder. Usually I have X and Y encoder. In fact, they are the same. They are the same networks. You encode X, predict, and create some embedding. And then you take some other information, this Z, that could be extremely trivial. It just tells me, for example, what I want to predict. Like if I have some part of an image, the Z can tell me just, okay, I want to predict this page or this page or this one, this or this one. Yeah, the Z is usually, like it can be this simple. Just the in position of what I'm trying to predict. I also encode the hidden stuff for some future or some other parts of the image. and I have the predictor there, which tries to predict it. Yes, so I feel like I'm not explaining it well enough, but if I have the joint embedding architecture, so I take 2 embeddings and they should be the same. The difference here is like the encoders are the same, but I have the predictor. So I encode the input, say, oh, I want to predict not just something in general, but I want to predict dispatch at the output by using Z. I have the predictor, which is a network which takes the encoding of the input and, in this case, the position, and tries to get the vector over there. And not just some vector representing the content by itself, but vector which represents the predicted hidden part of the data. And that's the difference. Jan LeCun says it works fairly well. It's data efficient. You can train it much faster on less data. In my mind, this makes complete sense. Myself, I haven't yet time to try it on our data, but I'm sure it has to work. And it's simple to implement. There's nothing weird about it. I tried it a little bit. The good part was it was fairly stable. Like it behaved well. It didn't explode or collapse or anything. And if you want
we can now detect features in almost any images.
And if you want to look at the state of the art in, at least the state of the art half year ago or 1 year ago in image processing, you can look, for example, at, Dino V2. This is self-supervised pre-training. It does those, it's contrastive, it does those transformations. So it basically learns representations robust to different transformations of the image. It's transformers, at least like in the paper they train transformers. You could train different architecture. And it's trained to produce local embeddings. So for at some grid, you get vectors at different positions. Of course, what you can do is you can color code similar embeddings with similar color. And what you can see here that similar parts of the DOEC have consistently the same representation in the feature space. And just from images, this pre-training learns embedding which are stable and semantically meaningful, and you basically get big transformer which you can use as a foundation model for anything. And this works. It works. As I'm saying, this is sort of the state of the art in image processing. There's one ingredient missing in my mind, and that's if you do this type of pre-training, it tries to learn everything, like every possible relation encoded in the data, any possible correlation, any possible everything. The point is that and that's not what we usually are interested in. We as people are interested only in small part of the possible information which is encoded in images. We perceive the world different than stones or birds or insects or whatever. The things which we are interested in are captured by language. So like for most purposes, what we can't say, we don't care about. Yeah, that's why language evolved. So one other way how to pre-train networks is to use language. It can be done at large scale. The first method which did that was CLIP. Does anyone remember what CLIP stands for? Sorry? Okay, yes. So contrastive language image pre-training. Yeah, it's contrastive methods, so it tries to put similar things together, different things apart, and it's on not just image versus image, but language versus image, so text versus image in this case. So what do? You go online, download millions and millions of images from the internet, not just the images, but also some text, for example, captions of like the alt captions or whatever. Filter it a little bit, you get rid of all the complete nonsense, and then you train on that. Yeah, you need several hundreds of millions of images. Again, you have to do this at large scale. Today, you would do it on billions of images. You can go, if I'm correct, doesn't matter. There are even like repositories like Lion, which is, they collected several billion images with these captions and filter that. You can do this pre-training yourself if you want to. And then what do you train? You train image encoder and text encoder. The text encoder here could be some kind of BERT, and I think in the original paper it was BERT. It maybe even was pre-trained already on text. I think it was. And you take some description, textual description of an image, run it through the text encoder, and you create a vector. You do the same with an image. Yeah, I take this puppy, run it through some convolutional network, transformer, doesn't matter. It just produces a vector representing that image. And I do that for a large batch of text and images, and then I do contrastive learning. CLIP was specifically trained using a sort of like softmax and cross-entropy loss, sort of. How it works, I take like embedding for image 3, embedding from text 3, do dot product on them, and this should be high. Like these vectors, this I3 and T3 should be ideally the same. Those vectors should be the same. So if they are normalized and I do the dot product, I should get ideally 1. And of course, if I multiply I3 with T2, they should be different. Like those are different. That's some random image with random text. They probably shouldn't have anything in common. Like I have billions of images. Yeah, so they don't belong together. And this dot product should be small. And you can take this row, for example. You can do softmax on that. And you can do sort of cross-entropy with this label being 1. Yeah, so this is the correct class. This image belongs to this text. Does anyone remember how this loss is called? It doesn't matter much, but it's really just softmax, cross-entropy. These vectors are normalized. Because they are normalized, this logit can be basically only from -1 to 1, which is not good enough. So there's usually some power on top of, so there's some constant power on top of that, which is learned as well, and which just allows these dot products to have big enough dynamic range to make this softmax as sharp as it's needed. And this works extremely well. And I'm sure that if you look, yeah, sorry? Yes. So, yes. So the question is, I'll just try to repeat it. I definitely can, in the batch, I can have like almost the same image twice. No one cares. Sorry, no one cares. This data is already so noisy that that's the least problem you have. Yeah, you have random images with random text from the internet. Some of them are complete garbage. Some of them, even if you do filtering, they don't belong to each other. And you know, this is, the goal is not to, it's the same as in masked pre-training. Like if I have BERT, you don't want, like there's not only one possibility. Like there could be different tokens in the position which you are masking. Yeah, you don't get perfect classification. And it's the same here. Like if, you know, this I3 could match with this text 5, whatever, okay, it can, but who cares in this sense? And really the data here is extremely noisy. There could be exactly the problems which you said, that in the batch I could have the same image even multiple times if whatever reason, whatever happens. And the goal is, you know, to make the network somehow understand the text and images and somehow connect them to each other. You don't looking at any kind of perfection. The point sort of is to use all the data in the world here to make these networks to understand almost any image, almost any text. So the goal is to get a robust network which is as general as possible, which understands sort of the images as broadly, semantically as we do. I don't have closed data set with 1,000 different labels. I get data set where my labels are all the words we use in our language. Yeah.
So the reason then why not instead of the softmax is equal function or something is used to is because it would get unstable or
Okay, basically you could use any contrastive loss here. You could use pairwise loss, triple loss, any loss which doesn't need like the representation of the identities. Yeah? It's something which doesn't remember anything. You can't use things like center losses if you are familiar with identification or metric learning. It doesn't matter. Yeah? This sort of works. What you are saying in my mind is right. You can set, this can be tolerant to these kind of problems. And you know, if there is something really similar, it's not too sensitive to that. It doesn't destroy the loss. It sort of gets average in all the data. And by the way, this is trained on extremely large, batches, yeah, like tens of thousands of pairs of images and texts, if you do it in large scale. And in my mind, like combination of this training on text and self-supervised training on those images themselves should be like the holy grail of computer vision. I would guess it should be the same in speech as well. Yeah, like we want the networks to understand the data, but we want the network also to understand what we as humans are interested in that data. And there are methods which do that, even in vision. So, when do you want to go home? I would spend maybe 30 or at most 40 minutes, and then I would leave. Would it be okay? Yeah? And I'll just continue, if you don't mind. Yeah, no problem? Okay. So let's have a look at some more interesting vision tasks than classification. By the way, what are the tasks in speech? Like you have transcription, you have speaker identification, language identification, diarization. So those are, sorry? Translation, that's transcription, so that's the same. No, anything else? Anything which is maybe less semantic? Definitely you have such. Okay, speech synthesis, okay. Speech separation, that's more interesting. And something more basic and close to these two. Speech enhancement. Do you have something which, this works on the signal itself? And do you have something which tells you more about the real world which produced those signals? Yeah, like if I have transcription, whatever that, or enhancement separation, that's, the separation tells me something about like the real world, that there were different speakers. But do you have something like which would localize the speakers, or which would, for example, reconstruct the room, the geometry based on signals in microphones, in some microphone array? Do you have something like that? Do you or not?
We do. You can estimate the reverberation time of the room, or...
Yeah, but it's not done too much, is it? Like it's not... Yeah, like you can't buy some device which would do that or something like that. It's what I'm trying to say that here it's, I think in vision, we are quite often interested in like not just understanding the semantics, but understanding like lower level stuff about the real world, like really the geometry, colors, whatever. No, it's not, the semantic tasks are important, but they are not the only ones. And I'll also try to look at some of those.
One of the more interesting tasks we worked on is from speech, can you estimate the height of the speaker?
From speech, but is it estimate height of the speaker? But is it on the sort of the tone and characteristics of the voice, or is it from for the direction?
There are certain vocal tract resonances which depend on the length of the cavity between the larynx and the mouth. And actually, some of them even depend on the sublaryngeal resonance. And that gives you the person, they call it the sitting height from the
Okay, yeah, but for me, these tasks are similar to something like person identification or something like that. They are, yeah, anyway. So let's look at some of the sort of more vision-specific tasks and network. The basic one is detection. Yeah, so it has some analogies in speech and text, definitely, but it's quite different. So, for example, imagine you want to localize this robot. You can do it with neural network. You can create very simple neural network which would take this image as input and produce 1, 2, 3, 5 numbers. It could produce probability that a robot is present in the image. To train that's simple classification task. You get a lot of images with and without the robot. and you train classifier. Robot is present, robot is not present. And then we want to know more. We want to know where the robot is. If the robot is there, where it is. And we do that as a simple regression task. So I can try to predict a bounding box. So let's say predict the position of the left top corner and the width and height of the bounding box, or maybe the center and the width of height and something like that. And I can easily train such a network. It would be almost a classification network. It would just have 4 more numbers at the output, which I would train using some regression laws, some mean sum of absolute differences or something like that. This still has some problems, like what would I do if I have multiple robots there? Who knows? The basic approach in computer vision is to do sliding window object detection. So if I want to detect more robots or small robots in an image, I can take a window, slide it over the input, and for each window I can ask, is there a robot or is it not there? And if it is there, where? Simple like that. Of course, if you did this, it would be extremely slow because you would have to run some network many, many times. So what actually happens, or what we do this type of prediction at the whole input at the same time. Yeah, so we take an image, run it through, let's say, convolutional network. It could be transformer. It doesn't matter much. And we create these types of outputs on a grid. Not just single output somewhere in the middle, but multiple outputs everywhere. If this is convolutional network, then this type of approach maps extremely well to convolutional networks, because convolutional networks, if you look at them, they basically compute each of these outputs the same way. Yeah, you can, because of the local convolutions which are below this output, they do the same operations over here, the same operations over here. And if those pixels are far enough apart, they don't talk to each other. They don't, like, if I had some object in the left corner, it probably wouldn't influence this pixel at all, this output at all. And that's what is reasonable, because if I want to tell if there is a cat over here or not, I don't really care much about the content up there. And in each of these output pixels, we just get, again, the probability if there's an object and what its bounding box is. So in this most simple case, I would get 5 numbers. Again, probability. If I have more classes, then I would get more probabilities and the bounding box. In general, you can, we call these single-shot detectors. Sometimes you will see YOLO as the name. On top of that, we have slightly more complicated detectors. So we have detectors which take the input, compute some features, and do this single-stage detection. Yeah, so they, based on some position, they say, okay, is there an object around that position or not? And then what these 2-stage detectors do, they take this predicted region and they try to reason a little bit more about that region. So what they do, they extract, really crop that region, extract the features in there. They do local pooling. And they run very simple network on top of those features extracted from that rectangle. This works slightly better, usually, than those single-stage detectors, but they are slower, more difficult. In general, these types of architectures which don't have just single output, but have multiple outputs, have this kind of architecture which takes input, reduces the size. This is the backbone. Makes it smaller, smaller, and smaller. And then they have one part which decodes it again, expands the information to some larger size. Yeah, for example, that classification network could have output, for example, at this location, which is 2 times smaller, 4 times smaller than the input. But if you take it to the extreme, you get to segmentation tasks, for example, where the input is the same size as the output, and you get prediction for each input pixel here. Yeah, so like in segmentation, where the prediction is for each pixel, the network tries to predict the semantic class of what's in the image at that location. The architecture which I'm showing here, it's UNet, or it's called hourglass network. These terms are equivalent, there's no difference. How the architecture really looks is, in this case, it's the VGG network. So it's always convolutions, pooling, convolutions, pooling, and so on until you get to very small resolution. This could be any other backbone. Yeah, it doesn't matter. Like you can replace it with ResNet, you can replace it with transformer, swing transformer, whatever. And then there is this upscaling again. Here it's sort of the same as the VGG network. So something opposite to pooling, so some type of that unpooling layer which I've talked about. It can be the very simple one which just replicates pixels, which does the nearest neighbor interpolation, enlarges the image in the most simple way. Convolutions, upsampling, and so on until you get to the output. If it was just like this, it wouldn't be enough, because if I go to this very small resolution, there I can reason about large parts of the image. I can understand if I'm looking at a horse or a cow. Both can be brown, the same color locally. They have hairs locally. And I need to understand if it's cow or a horse by looking at the whole animal. I need to see the head, I need to see the legs, not just the small patch somewhere on the back. And that's what I have here at the bottom at the very small resolution. So there I can understand what things are, really the semantics. But as it has low resolution, I lose information about spatial positions. Yeah, anything like, should this line be like at this pixel, or 2 pixels to the right, or 2 pixels to the left? And that kind of information can't be encoded at the smaller resolution. So these units, in general, they have these sort of skip connections, which take the information directly from the input at some at the same resolution level, and just copy them to the output. Yeah, so the semantic information, these networks go, at least should go, in theory, through this low resolution deep layers. But the information about exact geometry goes from the input through these skip connections. And the combination here could be different things. It could be, those tensors could be added together, but usually or it could be concatenation. There are different ways to combine them, but usually concatenation or addition. And if you have this type of architecture, you can really change the backbone, change the decoder, put different outputs at different resolutions. You can even do, for example, super resolution where you improve the resolution even more. There are many different, this is a basic architecture which you can use to solve almost infinite number of vision tasks. If we go back to that classification, it's here as well. I have input. It goes through a backbone, so like series of processing at the different resolutions. Then there is something which is called NEC. That's the decoder. In classification, we call it NEC. So we have backbone, NEC, and it ends at the head. And the NEC is sort of like, it tries to aggregate the information from the backbone. It could be as simple as the unit, which just goes in one direction, just concatenation, but there are more interesting architectures which feed the information down, up, down, several times, for example. And then we have heads. So for example, the dense prediction head. So for each pixel, I predict if there's sort of an object and its bounding box. In the detectors today, these types of dense prediction heads are multiple ones at different resolutions. So, and the low resolution one detects large objects. This one at higher resolution can detect many small objects. And if we want, we can have, here it's called sparse prediction. That's sort of additional head, which takes explicitly crops the detected region, takes just features from the cropped region and does some processing, like some additional network on top of that. That could be, the last one could be still detection, so predicting bounding box and probabilities to make, for example, detection better. But it could do different things. It could do segmentation. It could be localization of key points, like if it's a person, where does that person have his head, elbow, ankle, and so on. Yeah, so again, this is sort of general pipeline, and as anywhere else, it's easy to change output of a network, loss labels, and loss function. So whatever you want to predict about the bounding box, you can. If you wanted to train network which predicts age of a person, you can detect the person and predict it right away. This is from 2001. If you think speech and language is confusing, look at, for example, these detectors. The people don't have anything better to do to think about new things. So of course, we have tons and tons of different backbones, tons of necks, and even tons of heads or loss functions just to do detection. Of course, these backbones are general for image processing. These necks are general for whatever you do with images except classification. But these detection heads, for example, they are just for detection. And of course, all of this works that you can try any combination if you want. I don't suggest you do that. And by the way, there are libraries which implement many of these methods, and you can sort of really like combine them in any way you want. I usually really like the backbone and neck. They can put them together any way you want. If it's implemented in theory, you can do that on whatever these loss functions, they are not too easy to write, like detection. The data is structured, so it's not trivial. Like doing speech recognition is easier to write than to write loss function for object detection. So there's usually some problems. By the way, if you wanted to train an object detector yourself, the way to do that is like you can do that in 5 minutes. I would suggest there's a company called Ultralytics. They maintain basically sort of open source package for object detection. And so the package is extremely easy to use. It's sort of the state of the art in object detection if you don't want to do anything fancy. And it can be as easy as this. Yeah, from Python, you can just say, okay, I want to create a model. They have predefined models of different sizes. Then you say, okay, my data set is here. It has very simple structure. It's just text files with sort of CSV files with bounding boxes and images. And you just say, okay, train. You get the model as a result, and you can save it. And of course, you can predict things. You load either pre-trained model, run some images through that model, and show the results. That's it. And so if you ever want to do object detection, Ultralytics YOLO package is like 5 minutes from installation to training model to running the detection. And by the way, these networks don't need to train too long. In Vision, many of the tasks have to be fast. Yeah, so if I'm doing detection, the data which I need to sometimes process is, let's say, 1 megapixel image, 30 times per second. Yeah, so I have, if you do speech or whatever, there's much less data. Yeah, for images, it's hundreds of megabytes per second. At those, if we want to do any real-time processing in Vision, those networks have to be fast. Yeah, and for example here, even these detection networks, the small ones, you can train in 10 minutes. That they are extremely efficient to train. If you take the larger ones, you can do it in 3 hours on a single GPU. And we basically don't train models which you can't run in real time on good enough GPU. But it's 100 million parameter models, the large ones. By the way, of course, we use even like transformers are getting to Vision slowly, but they are not, for most tasks, they are not the state of the art. Sometimes they are, who knows? I just wanted to show that you can do, for example, detection with transformers as well. One of the methods is DETR, detection transformer, very simple abbreviation. How it works, it takes an image, runs it to some backbone. Here it's convolutional network, but it could be transformer. It doesn't matter. Takes those sort of token representation of those vectors through an additional transformer encoder, whatever. And then it learns to detect objects. But in this case, it doesn't detect like at the output at position 15, it tries to predict the object which is at that position, but it has fixed set of tokens which are not connected to the input at all, but they are learned set of maybe 10, 16, 30 vectors. The network itself decides what they should encode, what values they should have, but in this case, they are really constant trained vectors. There's a transformer decoder, which has cross attentions to the encoder, to the image itself. And at each of these tokens, it tries to predict single object. And of course, there's no, like, during training, there's no information like that this blue or this yellow one should detect this bird. There's no correspondence. Like, that's not in the training data. How these things are trained is, okay, I run the network on some image. I get some bounding boxes. They can be whatever. At the beginning, they are completely wrong. But then I look at my ground truth. So I get this bird. And there's sort of no bounding box predicted on it, but there's definitely one which is closest. Yeah, so what happens is during training, the loss function sort of takes the output of the model. For each ground truth, it finds the closest bounding box, assigns that bounding box to that ground truth, and says, okay, you should predict this object. And of course, it's in a way that's, it's one-to-one mapping at most. You can't have one bounding box predicting two objects or one object being predicted by two bounding boxes. So you start with some random outputs. During training, you match those outputs to the closest ground truth and train based on this mapping. DETR is quite old, and of course, because it's transformer, it has weaker supervision. This method basically needs more data. It needs to be bigger. It trains longer than, for example, those YOLO detectors. And if you look at object detection and processing, segmentation, whatever, these days we are trying to do even like completely general detection. Like what I showed before works on, you have a data set which has 20 different classes of objects, cats, dogs, people, airplanes, cars, whatever. And you train the detector on these objects. What we are trying to do as well is to create a detector which can detect anything. Basically, that it works in a zero-shot manner. So whatever image you put in, whatever text you prompt it with, let's say, I want to detect cat, person, and mouse, then it detects cats, persons, people, and mice in the image. And it's done sort of with the detector, as I showed the detector before. But let's say here, if I say it simply, the query tokens These ones, they are not fixed and trained, but they are extracted from the prompt. That's it. And usually there could be the text backbone that could come from clip and so on. And whatever. The rest of the image looks different, but it's almost the same. So a few more things. Segmentation, we've already have looked at it. In Vision, we have, but in the semantic segmentation, the task is to predict the class of pixels. So, like, this is a car, this is a person, this is a pedestrian sidewalk or whatever. But if for example, like here, I have too many people overlapping each other, it's just one big mass of people-ish region. I don't have individual people. To get individual segmentations of individual objects, we have task which is called instance segmentation. That's segmentation of individual instances of objects. Usually it's done with those, the last layer of, the second layer of heads, those sparse heads. So first it's trained as a detector, which detects region. Those regions get cropped from some feature space, feature representation. We run them through some simple convolutional network and predict the segmentation mask for that specific person. It's like the networks are extremely simple, extremely close, but it works well. As I said, we have networks which can do detection of anything, so open domain detection, just prompted by text. We do the same things for segmentation. So for example, there's a paper, it's by people from Facebook, segment anything. This is a model which takes image and then a prompt. The prompt could be, for example, points, like clicks on the object I want to segment, or a bounding box of that object, or some rough mask, or a prompt, text prompt, and it predicts the segmentation mask for that prompt. And actually, the network is fairly simple. In the case of segment anything, it has fairly large image encoder, like large transformer backbone, which creates a representation of the input image. And after this is computed, I can provide different prompts. So I can have points, box, text, which is processed by some encoder, and then there's fairly small network which predicts the mask based on the input features and the mask, the prompt, either the points, bounding box, or text. And it creates the mask as an output. What I like about this model is that here what they decided to do is to have very big encoder, which is however computed once, and then you can store these features and prompt the decoder with different texts, boxes, or whatever, and segment different objects. For example, if you use this model for interactive segmentation. So you can click on images, and you can get extremely fast segmentation if you are working with the same image. And of course, this can be done in with videos. There's, for example, segment anything 2. It's almost the same image encoder, prompt, which create, and mask decoder, which creates a mask. But because it's on images, on video, these outputs get compressed into memory. This is done with convolutional network, I'm not sure. And there's sort of like tokens stored in the memory, or it's vectors. And here, this memory attention, that's basically an attention layer which can look at the vectors which were stored from the history. And actually, this whole thing is differentiable, so it can learn what to store in the memory from the history, really by enrolling the prediction over multiple video frames. So before we go home or whatever, let's look at some lower level vision tasks. This is one of our own. In 2016 or 15, I decided that let's try to use neural networks for image enhancement. And so I can take something like the segmentation unit, which for segmentation it predicts probabilities of classes, but I can predict directly the values, the pixel values, like the colors of the pixels. And I can easily take a network, take bunch of nice images, apply artificial blur or other types of degradation on them, and train a network which take these blurry, ugly images as input, use the original nice images as output, and train the model and use it on real images to enhance them. This works quite well. It's actually a stupid idea, but because ideally this should be done in generative manner, we train it in like standard supervised discriminative way, which isn't such a great idea, but it worked. As in a similar fashion, I already said that you can do super resolution. You can, if I have that sort of unit, I can take, in the most simple scenario, I can take the image, put it in at a lower resolution, don't use this part, produce the output at a higher resolution. If I have training data which have this low resolution and high resolution pairs, again, I can train the network in supervised way to enlarge images. And this type of technology is used almost every day by billions of people, I would say. So for example, these days, anyone who has a newer NVIDIA graphics card, or these days even it's implemented by AMD or Intel, you have things like DLSS, which enhances images. Come on, where is it? Did I put the wrong timestamp there? Not wrong timestamp, but wrong video. So, what happens there is, so when you do rendering, you can do rasterization. So you take a rectangle with some texture, basically project it to the screen, and that's it, maybe add some direct illumination effects. Or you can do raycasting, ray tracing, or path tracing. Basically, that means, okay, I want to know what color is over there, and I send a ray. That ray intersects the wall over there. If I do path tracing, the ray somehow reflects randomly in some direction, and it sort of collects information about the illumination. Yeah, so even if I have light coming from there, maybe it still bounces around, and finally it hits that wall where I'm looking at. And these types of methods are extremely, the path tracing algorithms are extremely noisy. So what if you do this kind of rendering, you basically get the rendered information where you have like the texture, distance, maybe some reflective information about the surface. And then you have those noisy rays. So sometimes I cast a ray at that pixel, and it bounces outside, and it hits the sun, and it's extremely light. Sometimes it bounces here in the building, and it stays in the darkness, and it stays dark. So whenever you play some games which has this raycasting or path tracing, ideally you get the normal render plus some additional information which has good information about the illumination from path tracing, but it's extremely noisy. And what everyone does is they have neural network which takes these noisy rays, basically, the rendered images, maybe previously rendered frames, takes it all together and produces high resolution outputs with reflections, good illumination, and without noise. And it's the same thing. There's really a neural network which just takes these inputs, does something a little bit, and produces the output. And it gets rid of the noise. It gives you new frames. So even if I have rendering at 30 hertz per second, I get maybe 60 hertz at the output and so on. And we can do more than just detection segmentation. We can try to understand objects a little bit more. For example, for humans, do I have video or not? Okay, I don't have video, but never mind. So for example, if I wanted to know where people are and what are their poses, so where do they have their hands, legs, heads, and so on. One way to do that would be detect them and to predict the position of my hand, elbow, and so on. In 2019, these guys did it a little bit differently. What they did is that they predicted sort of positions of each part of the body, each joint. That's the word I was looking for. If you do that and you have just one person, then it's easy because you know how to connect them. I know where the neck is, and I know that I should connect it to this elbow and to the wrist, and I shouldn't do connection with, from that wrist to the knee. The problem is when you have multiple people. As if you have multiple people close to each other, you don't know which joint belongs to which person. So in their case, what they did, they also predicted a flow field, which basically gives directions. If I have those joints localized, in which direction should I go? So should I go from this shoulder? Should I go left, right, up, down? where. Where's the elbow which is connected to that shoulder? Yeah, so they trained it to produce another additional layers which have X, Y directions, vectors in each pixel, which tells you from, for example, from the elbow, how to get to the correct near wrist, which belongs to that elbow. And so it's predicting structured information, but still the output, it's predicting skeletons, but still the output is just images with some information. And we can do things even predicting dense pose, like in this case, where in each pixel, the network predicts the 3D surface coordinates of, let's say, the model of the person. And let's look at really like last two things which are really low level. One of the basic tasks in computer vision, if you are processing videos, is to understand how things are moving. Come on. I forgot maybe 2 or 3 slides which have those examples yesterday. So anyway, so what does it mean? It means that I need a network which takes 2 images from a video sequence, and for example, for the first image, in the output, I would like to get information where the pixel is in the other image. So I want to get XY coordinates, how to go, where to go in the other image to get the same object, same real world coordinate, basically. This is also, for me at least, it's funny story from computer vision, because people actually used to train these models on extremely weird data. You can't label videos by hand and say, okay, this point moves this way, and it was in this frame, it was here, and that in the next frame, it's somewhere else. You can't do that. It's not practical. But you can render things. The first data set, which is still used, is called flying chairs. And basically what they did is they took 3D models of chairs, random photos as a background, and they let the chairs randomly fly over that background. It's completely weird, completely like crazy data set. You will never see flying chairs in the real world. But you can train neural networks on this data set which work on normal images. I'll show something. I have to find something anyway. This looks weird. Yeah, so you can get something like this. You can see the points that they track the drones perfectly. A nice cow. And this looks really weird. Deep flow looks weird. I have nice videos which I did myself. Basically, the color there encoded the movement. Anyway, why I'm showing this? I said that we had those networks which had convolutions, attentions, and so on. These optical flow networks are slightly different because they tend to use different layers, different operations, slightly. If I look, for example, at CRAFT, at this network, what it does, it takes two images, processes them using some backbone, so something like ResNet, and creates a feature representation for each of those images. So let's say every 8 pixels, you get a feature vector. But because when you do optical flow, you don't care what's in the image, but you just care how it moves. And you care that, okay, this looks the same way as it looked at some different point and the previous image. So you actually care about similarities. In our world, we can say correlations. So what actually these networks do, they take all the vectors from one image, from the other, and they correlate them. Not all of them, but in some local neighborhood, like let's say I take this part of the image, I take this vector, and I compute correlation with all the vectors from the neighborhood. And they create, in this case, for the cost volume. So you get XY coordinate from here, XY, and the other XY coordinates from the other. And it creates 4-dimensional cost volume, how similar each part of this image is to each part of the other image. And this cost volume is processed further. And so this is, I'm showing this mainly because this is an example of a network which is built specifically for the task. And really the idea here is I don't care what is there, but I just care how similar this part of the input is to all the other parts, because that's important for the task I'm trying to solve. And I think it was enough. Just one, maybe one slightly, last slide, and final idea. When you do some machine learning, sometimes at some instances you can do really weird things with loss functions. In computer vision, we have really weird loss functions. For example, and it's even in, for example, physics. Like these days, you can get differentiable physics engines. You can propagate using some physics simulations backward. We can do it through rendering. So, for example, we can optimize geometry based on images or the other way around. What I have here is an example of a network which basically is trained to, but if I give it a single image, it can sort of decompose that image. And we call those decomposition intrinsic images. In this case, the network tries to predict colors. So like the real colors of the surface of the objects in the real world without illumination. Then it tries to predict illumination, so like the direction from where the sun is shining, and also the geometry, the normals. And of course, for this, you can't get ground truth. You can't, you can little bit, like there are devices you can go in with device this big, something like if I took this and if I wanted to know what is the color of this wall, I could go and put the device there, hold it for 2 minutes, measure the surface, and then go here and do that. That's not practical. We can get the geometry sort of using, for example, laser scanners, but again, they are not perfect. It's not easy. What these guys did, they said, okay, I will just use images. So they gathered a data set of a lot of images. In those lot of images, they found photos of the same object, like, for example, this is, what is it, Prague, how it's called? Astronomical clock. Yeah, Prague astronomical clock. And the loss function here is, or the network here, given this image and this image, let's predict the color from those 2 images. Let's predict the normals of the surface. Let's predict the illumination for each of those images. And now let's do the loss function. And the loss function here is, okay, I predict color from one image, geometry from the other. Using this, I can basically render the object as if I saw it from the other image. So there's renderer that produces an image, basically, which takes color from this one, geometry from this one, and I can compare them. And if everything works, I should get exactly this second image. And of course, you can do it the other way around. I can take colors from this, geometry from the other, and see if I get the correct image. With the illumination, with everything. So, and this is example of a loss function, which allows me not to run around with laser scanners, not to run around with measuring devices, and still I can train a network which predicts colors, illumination, scene geometry, without ever creating ground truth for that. And it's complex, it has differentiable renderer in it, but it can be done. Okay, so that's it. I don't really want to hold you here longer. Like, if you wanted to, we can, but I don't think we need to. What I've skipped is what we basically do with text recognition, which may be most interesting to you. But anyway, it's very shortly, we do the same things as with what we do in speech. So basically, if you know Whisper and you switch the audio input for images of handwritten documents or other documents like these ones, that's how we do handwritten recognition, and it works really well. So that's the last few slides. If you want to see me talk to me about some vision things or text recognition or whatever, you can come to see me. I'm in building Q, office Q201. And of course, you can see me in kitchen at our department, where I'm making coffee several times a day. So that's it. If you have any questions, go ahead. Yes, I can share the slides. It's online on Google Drive. I'll give it to someone. I'm not sure where you are putting the slides.
I also asked for the slides from this morning.
Yeah, so should I send it to you? Okay.
Link is perfect.
Yeah. By the way, feel free to write comments to the slides. You can comment them. Yeah, if you think something, if you have some questions or something should be improved, let me know.
Thank you for the great talk. So that in this just the OCR part, in this example, you just pass a single sentence image, so it almost looks like the spectrogram or something. But in the case of the document level, there's a sentence is folded. Sometimes the title and the content is not well aligned. So is there any specific technology to handle the document level unconstrained papers or something?
Okay, I hope I understand your question right. So when we do OCR, we first detect lines. Then we have some reading order, and we read the lines either line by line or like concatenated text lines. But by the way, today you have also like sort of end-to-end systems where even GPT-4 does that, or models like that. Like those are, let's say, multimodal large language models, which take the whole page as an input, like splits them into tokens and use it as a prefix for, and they generate the content. Yeah, so.
Okay, so they're traditionally first segmenting the document into the line by line, then pass the OCR.
So most of the systems work on single lines, especially like it's hard to do like full page processing on newspapers where you have 1,000 lines and it's like 5 megapixel image, like, and the text is tiny. There's a lot of it. But these days you have those end-to-end systems, which are really vision language models. They work, but they definitely hallucinate sometimes. So you get transcriptions which are not there. They miss something, so they are not that reliable. It's hard to get position because usually you don't need just the text, but also you need to know where it was in the input, which is harder to do with those end-to-end systems. So yes, even now the state-of-the-art OCR and handwritten recognition models do the segmentation first, and then the transcription, which then is almost the same as with speech.
I see. Thanks so much.
In the last, one of the last slides, you were showing this model with these different costs. So that kind of dissects, this one, dissects the geometry, lighting, and something else. So how do you force the model to know that this is geometry, this is lighting, this is colors, and this is structure? Because I can imagine a model that learns different things, but how do you relate these things to the physics?
In this case, it's really like how the loss function is structured. So it's really renderer, where basically the color is like different input and different operations happen to it than with the geometry, illumination, and so on. Yeah, so there it comes naturally from the loss function itself.
Okay.
Otherwise, I would guess, this is actually a good question, because sometimes this happens that I'm not, definitely, and sometimes when I trained some models where there are more solutions, like the models can, even, for example, here, yeah, so OCR, good example. One of the methods which do OCR is CTC loss. It's used in speech recognition as well, but basically how it works is for each position of the image, it predicts the text. It predicts and you don't train it with labels, aligned labels. So it could predict those labels anywhere. Yeah, so it could put all the characters at the beginning of the sentence, at the end, and we use models which can do this rearrangement fairly easily. Yeah, for example, once we trained Arabic text OCR, or handwritten recognition, and we sort of forgot that they write from the other way around. So, of course, all our labels were in the wrong order. Yeah? And the network easily trained to predict it, even in the wrong order. So it's not just learn to read the text, but also to flip everything. And these models can do that. They could easily predict the labels anywhere at completely different locations than the characters actually are, but they don't do that. They predict the characters at exactly almost perfectly aligned positions to the input. And this happens often, quite often. Like, I would say, the networks in training always find the easiest solution. So we are lazy, nature is lazy, machine learning is lazy as well. So if there's a simple solution, you'll get it.
Okay, thanks. Everyone is dead already. So I would like to thank Michal again. And well, thank you very much for surviving the third day of our summer school. And we continue tomorrow in the morning. Attention, we are at a slightly different location. So is the lecture room G202, which is just next building, and someone will take you there from Mensa in the morning. It's not far from here. Okay, and thank you very much, Michal. And that's it for today.